Hello, Accelerated Chemistry students. This is Miss Crystal Foley, and this is your Chapter 6, Section 3 notes over periodic trends. Now, just going to warn you, this is going to be a little bit of a lengthier one, but we got this. You can do it. So here we go. Let's first talk about periodic trends in general before we talk about the different kinds of them. So we know that periodic properties are characteristics that all elements on the periodic table share. So there are group trends, that is the patterns in a property as one reads down a group. And remember, this happens because of the number of electrons that are in the outer shell. This is also apparent because of the fact that we've talked about this. All of the elements in the same group, their electron configuration ends the same way. So right here we have group 1 elements, lithium, sodium, potassium, rubidium, cesium, and francium. They all end with S first. And beryllium, magnesium, calcium, strontium, barium, and radium all end with S squared. So they're going to behave very similarly. So there are going to be two factors that affect these group trends: the attraction between the nucleus and the valence electrons. So remember, the nucleus is positively charged. This is because we have protons and neutrons in the nucleus. Remember, protons are positively charged, neutrons have no charge. So those positive protons are going to be attracted to the valence electrons, which are negatively charged. And the valence electrons, remember, are the electrons in the outermost shell. So you have a positive nucleus pulling in or attracting those electrons in the outer shell. The second thing that's going to affect these group trends is the electron shielding. So what does that mean? Putting layers around the nucleus. So the more layers you have around the nucleus, the more the positive pull of the protons is going to be blocked by the electrons that are closest to the nucleus. So that's what we call shielding. Those inner electrons, the electrons in the first ring and the second ring, are going to block the attraction between the nucleus and the electrons that are the furthest away. So if we were to look at this picture, this is going to represent the size of an atom. So when we're looking at these shells, so each circle represents an energy level. As each energy level is added, the distance between the nucleus and the electrons increases. And this is going to weaken the attraction between the nucleus and the valence electrons. That should make sense. The further you pull a positive end of a magnet and a negative end of a magnet away from each other, the less they're going to be attracted to each other. So when we're talking about periodic trends, we've talked about ones that are basically going to be affected by the groups and how that works. So now let's talk about a period. Remember, a period is the row on the periodic table. So period trends are patterns in a property as one reads across a period or a row. And there is one factor that is going to affect the period trend. So remember, as one reads across the period, across the row on the periodic table, the number of protons increases from element to element. So that means that the positive charge of the nucleus is going to be stronger as you go across from left to right, because you're adding one more proton. So you have more positive charge. And so that's going to have a stronger attraction on the electrons that are in the furthest shell away. But remember, if you're adding and going across, you're adding protons, those electrons are in the same energy level. They're in the same ring around the nucleus. So the distance is not changing. The pull is going to be stronger because we're adding more protons as we go from, say, for example, boron, which has 5, to carbon, which has 6, to nitrogen, which has 7. So if we were to look at this, okay, if we look at the period trend this way, As the positive charge increases by adding a proton from element to element, the attraction between the electrons and the protons is much stronger, pulling the electrons closer to the nucleus. So when we talk about the different properties, think how this attraction is going to affect that property. Okay, so now let's start. We're going to talk about several different periodic trends that we see on the periodic table. I'm going to go through point by point, and we're going to explain the what is the trend across the period, down the group, and also the why. So be very particular in your notes. So let's start about the first one, atomic radius. Atomic radius is half the distance between two adjacent atoms. So basically, what is it? It's the size of the atom. So if we look at this picture, the radius would be between the center of that atom on the left to where those two atoms are touching. That would be the radius. So from the center of the atom to the furthest most electron. So as we go across a period, this is across the row, the trend is going to decrease, meaning the size of the atom is going to get smaller. Why? Because the nuclei have a greater nuclear pull, a larger positive charge as you go from left to right. Remember, as we move across a period, we're constantly adding one more proton, one more positive charge. So that's going to pull the electrons in closer and closer and closer. So that's going to make the size of the atom smaller and smaller and smaller. So if we were to look at this, comparing aluminum to chlorine, we have less nuclear charge, 13 protons in aluminum. We have more of a nuclear charge in chlorine, 17 protons. So look at how that atom shrinks. It becomes smaller. Now let's talk about going down a group. The trend is going to increase. Why is the atomic radius going to get bigger as you go down a group? Well, think about as you go from period 2 to period 3 to period 4. You are going to increase the number of energy shells, the number of rings around the nucleus. So that size is going to be bigger. You're adding a whole nother shell around the nucleus. So another layer, increasing in size. So as we look from lithium to sodium to potassium, lithium has 2 rings around it. Sodium has 3 rings around it, and potassium has 4 rings around it. So the size of the atom is going to get bigger and bigger and bigger. So if we were to look at this overall, atomic size increases going down and decreases going across the periodic table. So now let's talk about reactivity, because reactivity and atomic size go hand in hand. So for metals, the reactivity is going to decrease going across a period and increase going down a group. Why? The larger the atom is, the weaker the nuclear pull is going to be on those outer electrons. And so that means that those outer electrons can be lost easier so that the atom can become more stable and have that noble gas configuration. Nonmetals, the reactivity is going to increase going across the period, and it's going to decrease going down the group. The reason being is because the smaller the atom is, the greater the nuclear pull, the greater that positive charge is going to be in the nucleus, attracting those electrons, and it's going to be easier for them to attract electrons to gain that noble gas configuration. Okay? Remember, these are straight memorization facts. Okay. Now we're going to talk about ions. Some compounds are composed of particles called ions. An ion is an atom or a group of atoms that has a positive or negative charge. So an atom is electrically neutral because it has equal number of protons and electrons. We've talked about this. Should be nothing any that we haven't talked about before, nothing new. So for example, an atom of sodium has 12 positively charged protons and 11 negatively charged electrons. So if we were to add the positive 11 and the negative 11, the overall charge of the sodium atom would be 0. Makes sense. Positive and negative ions form when electrons are transferred between atoms. So atoms such as metals, sodium's an example, tend to form ions by losing one or more electrons from their highest occupied energy level. We've talked about this. Elements in group 1 want to look like noble gases. So what they do is they lose their outermost electron. So everybody in group 1 will become +1 charged. Group 2, they have 2 electrons in their outermost energy level, so they like to become +2 charged. As you move across the period, you go from metal atoms to non-metal atoms, so then your charges is going to shift. Nitrogen's group likes to be -3 because they only need to gain 3 electrons in order to be stable. Oxygen likes to be -2. Fluorine likes to be -1. So in a sodium atom, the number of electrons, 10, is not equal to the number of protons, 11. So sodium will lose an electron and become positively charged because we have more positively charged protons than negatively charged electrons. So when sodium loses that 1 electron, it'll be a +1 charge. So we call this positively charged ion a cation. Notice the T in cation. It looks like a positive sign, so cations like to be positive. The charge for the cation is written as a number followed by a plus sign. And if the charge is 1, we don't normally write it. So it'll be just Na+, and we know that that means it's +1. Atoms of nonmetals, such as chlorine, tend to form ions by gaining 1 or more electrons. So in a chloride ion, the number of electrons, 18, is not equal to the number of protons, which is 17. We have more negatively charged electrons than positive protons, so the chloride ion is going to have an overall negative charge. So one more time, if we gain electrons, nonmetals love to gain electrons, you're going to have more negative things, anion, more negative things, so you're going to have a negative charge. So the negative charge ion, like I said, is anion. You have that N in there, it's going to be negative. And again, it's going to be the number followed by a minus sign. So let's talk about ionization energy. This is another trend on the periodic table. So this is the energy required to remove the most loosely bound electron from a gaseous atom. The most loosely bound electron is the outermost electron. So let's talk about the trend. So across a period, the trend's going to increase. Why? You have more protons in the nucleus. It's going to be holding onto those electrons more, so it's going to take more energy to remove that electron. One more time, greater nuclear charge, greater nuclear pull on those electrons, so it's going to be harder to remove them. So down in group, the trend is going to decrease. Why? Because when you increase the distance between the outermost electron and the positive nucleus, you're going to have less of an attraction between those opposite charges. So a less nuclear pull, it's going to take less energy to remove that outermost electron. So larger atomic size, less attraction to that nucleus from that negative electron. Smaller atomic size, it's going to have that stronger pull. It's going to take more energy. So we've talked about 2 trends so far. We've talked about atomic radius and ionization energy. Now let's talk about ionic size. So during reactions between metals and nonmetals, metals tend to lose electrons and nonmetals tend to gain them. This transfer of electrons has a predictable effect on the size of the ions that it forms. Cations are always going to be smaller. The positive ion is always going to be smaller than the neutral atom because when the cation loses those outer electrons, think about it as shedding a layer around the nucleus. So the atom is going to shrink and become smaller. Anions are opposite. Anions get larger because you're going to have more electrons in the outer shell, which means that those electrons are going to have to spread apart more to get away from that electron-electron repulsion. So ionic size tends to increase from top to bottom within a group. That should make sense. As you get further down in a group, you're adding more shells, so that will make sense. And the size of the cation and anion will decrease as you go from left to right across the period due to nuclear pull. So let's talk about group trends in ionic size. So for each of these elements, the ion must be smaller than the atom. So the radius of the Na ion is about half the radius of the Na atom. So when the sodium atom loses an electron, the attraction between the remaining electrons and the nucleus increases. So this is going to pull those outermost electrons in closer. Remember, when elements lose electrons, they end up having more positive things than negative things. So they're going to hold on to those negative things even more, pulling them in even closer. So metals that are representative elements tend to lose all of their outermost electrons during ionization. Therefore, the ion will have one fewer occupied energy level. So the size of the atom, remember they shed that outer energy level, is going to shrink. Should make sense. Now let's talk about it for nonmetals. Nonmetals are opposite. Remember, their size when they become an ion increases. And this happens because as the number of electron increases, the attraction of the nucleus for any one electron is going to decrease. And also remember, you're adding more electrons and you're adding them into this same ring around the nucleus because when they get added into the highest ring. And so they're going to want to spread out because you're going to have that electron-electron repulsion, which is going to force the ion to gain in size. For periodic trends in ionic size, from left to right across the period, two trends are going to be visible. There's going to be a gradual decrease in the size of the positive ion, and there's also going to be a gradual decrease in the size of the negative anion. So if we look at this, we can look and see how these ions, if we're looking at the size of the atom versus the size of the ion, notice the chart at the top will show you which one's the metal atom and which one's the cation and which one's the nonmetal atom and which one's the anion. Look at the different sizes, okay? The cation is always going to be smaller than the neutral atom that it came from, the neutral metal atom. The anion, the negative ion, is going to be always larger than the non-metal atom that it came from. So, size of the cation is going to decrease and the size of the anion is going to decrease as you go from left to right across the period, and it's going to increase as you go down the group. Remember, straight memorizing these trends. Okay, the next trend that we're going to talk about is electron affinity. After this, we have one more. We got this. So electron affinity is the opposite of ionization energy. Remember, ionization energy is the energy needed to remove an electron from a gaseous atom. Electron affinity is the energy associated with the addition of an electron to a gaseous atom. So now we're adding electrons. So across the period, the trend is going to increase. Why? Because we're adding an electron, but we also have a stronger nuclear pull that's going to make it more easier to attract that electron. So greater nuclear pull, we're going to want to pull onto that electron more, which also should make sense. As you go from metals to nonmetals across a period, you have things that give up their electrons on the left side, which are your metals, and things that accept your electrons, which are your nonmetals on the right-hand side. Down a group, the electron affinity is going to decrease because as you have a larger size, you're going to have less of a pull on those outer electrons. So the attraction of those outer electrons is going to decrease. So remember, the distance between those oppositely charged particles gets larger as you go down a group. So that is going to make the attraction weaker. And this is the last periodic trend, electronegativity. Electronegativity is the measure of attraction for electrons. Fluorine is the most electronegative element and it's on a scale of 4.0. So the closer the atom is to fluorine, the higher the electronegativity is. And these are actual numerical values. All right, so let's talk about these trends. So across the period, the trend is going to increase. Why? Because you have a stronger pull on the electrons, and so you're going to be able to attract the electrons easily. So your electronegativity is going to increase. Again, these reasons why we talked about them at the beginning of the video, they should all be repetitious. Greater number of protons, stronger nuclear charge, it's going to pull those electrons in further, and it's going to make these trends happen. As you go down a group, your electronegativity is going to decrease. Why? You're going to have a larger atomic radius, less nuclear pull on the outer electrons, so your electronegativity is going to decrease. Again, this is nothing that I have not said before in this video. It's constant repetition, but you need to be able to distinguish between these. Okay? So let's look at a summary of all the trends we've talked about. Metallic character we talked about in a previous video. As you go across a period, it's going to decrease. That should make sense because metals are on the left side of the periodic table, non-metals are on the right side of the periodic table. So as you go from left to right, your metallic character, how metal-like your elements are, decreases because you go from metals to non-metals. As you go down a group, it increases. Atomic radius decreases as you go across the period. Stronger nuclear pull. It's going to pull those electrons in closer. And it increases as you go down a group because you're adding more shells around the nucleus. So the distance between the nucleus and the outer electrons increases. Ionization energy is going to increase, go across a period. It's going to, remember, ionization energy is the energy needed to remove an electron. The closer those electrons are, the tighter they're held to the nucleus with that stronger nuclear pull, the more it's going to take to remove them. So that's why going across a period, it increases. Going down a group, it decreases. The attractiveness between the outer electrons and the nucleus is less, so it's going to take less energy to remove them. Electron affinity is the opposite of ionization energy, remember? And so it's going to increase going across a period and decrease going down a group, should make sense. And electronegativity is going to increase going across a period and also decrease going down a group. So these are all of the trends. And in class, you're going to be working on that flip book, which will help you keep everything straight. And as always, all of the information on these Google Slides has been acquired and adapted from Pearson Chemistry's 2012 edition of the textbooks, Resources CD, and pearsonchem.com. Thank you so much and have a good night.